For this problem, we have a cylinder capacitor. And we know it's a capacitor because it has a charge or a charge density of positive lambda and a negative lambda shell around it. So when they're equal and opposite charges or charge densities, we can call it a capacitor. The electric field on the outside is going to equal 0. The electric field on the inside is going to equal to 0. And we need to use Gauss's law to figure out the electric field in the center, which then will get us the potential in the center. So in this scenario, we're trying to find the expression for the capacitance, which is charge over delta V. We're not given charge, but we're given lambda, which is equal to charge over length. And we can solve for delta V given that lambda as well. So the first thing we're going to do is we're going to use our electric field on the inside to figure out what the changes in potential is on the surfaces from the inner surface of B to the shell at A. Okay, so Gauss's law is how we find our electric field, which is the enclosed integral of E dot dA is equal to the Q enclosed over epsilon naught. The area is going to be a Gaussian surface that is somewhere in this center here. And then we're going to just give it a predetermined length of L. So in this case, my Q enclosed is going to be lambda L, and I can plug that into my expression. The area, when we enclose the area, is going to be this curved surface on the outside, not the end caps. So that equation is 2 pi RL with this inner radius of R. And Q enclosed is lambda L over epsilon naught, which allows us to reduce. And now we've got an electric field, which is inversely proportional to R, which is what we expect for the electric field on a cylinder. Here, we are going to use this expression to solve for delta V, because delta V is equal to the negative integral of E dot dr. And we're going from the outer surface B to the surface of the inner the inner cylinder. So it's going to go from B to A. I'm going to erase this electric field equation or electric field variable and plug in our electric field equation of lambda over 2 pi epsilon naught R. Now, this is the first time we're seeing this relationship. So for those of you who have not taken calculus yet, I'll show you where to find it in the equation sheet. We'll do more of these in a future unit. So I didn't want to emphasize it too much for the sake of one single problem. But if you're working on this, you're definitely going to need to know how to do this calculus. I'm not going to put it on test, but it'll be good to kind of follow along this process. So I'm pulling out all my constants, lambda, 2 pi epsilon naught, and I'm integrating from B to A of 1 over R dr. So if you go into your equation sheet, it doesn't look similar to what we've seen, but this expression is the same as dx over x. If we have a constant in there, which we don't in this case, then we would just include that in our integral once we solve. But in this scenario, whatever the denominator is, if that's where your variable is at, the answer is going to be ln of this expression. So this would equal ln of x. And then if you had limits, you would plug in limits. In this case, in our case, it was B to A. And I'm going to go through that process, but I just want you to realize that this expression looks more complicated, but most of the time we're going to see it as the integral of 1 over x dx. In fact, I'm going to erase this just so that the notation is more familiar to you guys. This is the same thing as 1 over x times dx. So let's go back to our expression. We've got 1 over r is our variable, and we're integrating with respect to dr. If we look on our equation sheet, we know that the answer to that is, I'm going to write out all my constants, ln r. And our limits are from b to a, and all we have to do is plug in our upper limit minus our lower limit. So negative lambda 2 pi epsilon naught ln A minus ln B. Now, because I don't like extra negatives, it's always good to simplify by factoring that negative into each side. And I end up with a positive 2 pi epsilon naught, and my ln B becomes positive, and my ln A is now my negative. So I'm going to switch them. And in this scenario, when you have ln minus ln, this is a property you should have already learned in your prior math classes, but that can turn into a division, ln b divided by a. Now, we still have to plug this into our capacitor equation. So this is delta V. Our capacitor is charge over delta V. Capacitance, we don't have Q, but we already established up here that Q is equal to lambda L, and therefore I'm going to plug in lambda L over lambda over 2 pi epsilon naught ln B over A. And then I'm going to multiply by the reciprocal. So ln B over A is a value, so I can't multiply that by the reciprocal to get it in the numerator, but I can multiply this by the reciprocal and get lambda L times 2 pi epsilon naught over lambda ln B divided by A. My lambdas cancel out, and we should have this expression somewhere in our answer, 2 pi epsilon naught L ln B over A, and that is right here. So a long process. This you should know how to do, finding the electric field of a cylindrical charged conductor. And then taking the integral of that is a new calculus property, but it is in your equation sheet, and we are going to cover a lot more of this once you've learned about this integral in calculus.